Hello everyone. Today we are going to talk about SQL Server indexes. Indexes in SQL Server serve similar purpose as they do in physical books. In the physical books, we find index pages at the end of the book. For example, let's take a large book, let's say a book with over 300 pages, which is written on technology. But we only want to read pages written on databases. So if we don't have an index, we would have to read the entire book to find pages written on databases. But if that book contains an index, we can simply read the index and find the page numbers on databases, and then directly turn to those pages and read them. Similar way, indexes in SQL Server provide a method to retrieve data much faster way and serves your query more quickly. As example, let us consider a scenario where SQL Server is looking for all the employees starting with letter D from the employee table. If employee table doesn't have an index like our book does, SQL Server will have to read the entire table to find employees with name starting with letter D. But if it had an index on employee table, it could just read the index and jump straight to employees it required directly and present the result set quickly to the user. Index is a data structure which is linked with a table. In a way, you can call it a small copy of the table, which has data arranged in a different way than the main table. You can have multiple indexes on a single table. Each of these indexes will arrange a copy of the table data in a different way, so they can satisfy different queries very quickly. There are several types of indexes in SQL Server. You can have tables without indexes. When a table doesn't have an index, it is called a heap. In a heap, there is no order to the data, and they are stored as they come. Next, we have clustered indexes. When you create a clustered index for a table or for a heap, the table or the heap is rearranged in the order of the index. So basically, table becomes the clustered index because data in the table physically rearranged to match the index. For example, let's think about a table with employee data. Then we create a clustered index on that table. Let's say we create a clustered index on employee ID column. Then we get a table which is physically sorted on employee ID. This is a clustered index. You can only have one clustered index per table because table data is physically structured on clustered index. When you specify a primary key for table, SQL Server automatically creates a clustered index on that column. Let's say we have a lot of queries based on employee name. So we need to access name very frequently. For example, we need employees who has name starting with letter D. But as it stands now, we need to read the entire table to find those employees. In order to ease the pain for SQL Server having, we can create an index on name column, but leave the physical structure of the table as it is. To do this, we can use non-clustered index. Non-clustered index will create another structure linked to the table. It is kind of small copy of the table, but arranged in a different order. Though we only specify name column in the index, SQL Server always put the primary key of the table on the non-clustered index. so that it can relate row back to the original table. You can have many non-clustered indexes as you like on a table. However, more index you have, more data SQL Server will have to add, update, delete when you add, update, delete data from the table. Because SQL Server have to update non-clustered index as well as the table data. Next we have a unique indexes. Unique index is a special type of index. It just tells SQL Server column specified in the index cannot have duplicate values. You can have clustered and non-clustered unique indexes. By default, primary key constraint create a unique clustered index and unique constraint create a unique non-clustered index. For example, in our employee table, we can create a unique constraint on email column. Then users won't be able to insert duplicate values to this email column. Also, this tells Query Optimizer that data in this email column is unique. This information is vital and used when Query Optimizer come up with execution plan. Filtered indexes are special type of non-clustered index where we only store data frequently required from a column. For example, if we have location on our example employee table and most queries are based on location equals, let's say, London, we can create a non-clustered index filtered only for employees who are in London. Having a filtered index is efficient because you don't need to store the entire value collection for that column in the index. So this is a small index. This makes index especially useful for optimizers because it can use small set of data. There are many other type of indexes in SQL Server. For example, you can have full text indexes, XML indexes, spatial indexes which deal with geometric data, column store indexes which is again a vital kind of indexes which we are going to talk about in different module, and hash indexes which are in OLTP in memory tables. We are not going to talk about these special type of indexes in this module. Next, let's take a look at the index storage and architecture briefly. In this module, we are mainly focused on row store indexes. We will discuss about column store indexes and their storage structure in separate module. Row store indexes are organized into data structure called B tree. In fact, it's called B plus tree, an enhanced version of the B tree. B plus tree is a data structure used to efficiently do insert, deletion and update. And it also helps to efficiently search data in tables and indexes. So that's why this B tree plus structure is used in SQL Server. As we learn in other modules, data in SQL Server are organized into 8K pages. So B plus tree also constructed using 8K pages. Each page in B plus tree structure is called a node. Top node of the index is called root node because it's in the root of the tree. Very bottom nodes of the index is called leaf nodes because they are like leaves in the tree. There can be multiple levels of nodes in between root node and leaf node. They are called intermediate level nodes. These intermediate level nodes link root nodes and leaf nodes together and allow SQL Server to travel from root node and find data it requires. Each of these nodes are doubly linked, which means SQL Server can go back and forward from one node to another in the same level. Okay, we have learned theories around SQL Server indexes. Now it's time to take a look at indexes in action. To do that, let's consider our employee table example. Right now, employee table is just a heap. There is no order to the data in the employee table, as you can see on the screen. Let's assume we need an index on employee ID column. We can also assume employee ID column is the primary key of the table. When you define a primary key on the table, SQL Server automatically creates a clustered index on the table. Or you can create a clustered index using a statement like this one. So what's in the statement? First, we are going to create a new index. So it's create keyword, and then we specify what type of index, clustered index, and then we specify name of the index, and after that we say on what table, employee table, and then we specify inside the brackets we specify which column we want the index on. When SQL Server creates a clustered index, it puts all data pages at leaf level node. Let's assume in one 8K page in leaf level can only fit 5 records from our example employee table. However, in reality, this will be different based on size of the row and data in the column. So it's just an assumption for this illustration. Okay, then we should be able to see data in leaf level like this. As you can see, all 20 records are distributed among 4 8K pages. Note, because nodes are doubly linked, indicated by those arrows, you can traverse or read from one node to another both forward and backward direction. Let's move to intermediate level of our index. Intermediate level nodes doesn't actually contain data, but they contain pointers to actual data pages. As you can see, we have 2 intermediate level nodes. Left one contains pointers to records 3 to 30, employee ID 3 to 30, employee ID. Since those records are in 2 different leaf nodes, there will be 2 distinct pointers in the left intermediate node. Same with right one as well. It contains pointers to record 33 to 60. Intermediate level pages are also doubly linked, making going within those levels easy. In complex data table, you will have multiple levels of intermediate nodes. Finally, we can see root level to complete the picture. Root node has pointers to intermediate level. In our example, records 3 to 30 are pointed to left side intermediate node, and 33 to 60 records are pointed to right side intermediate node. Okay, now let's take a look at how index seek operation is carried out in this data structure. Let's say you want to seek record number 26, Ethan Hunt. So our query will be like this, and then we start from the root node and then come to when we look at the records in the pointers in the root node, we see that 26 is in the left side of the intermediate node. So we go to the left intermediate node, and from there we see that the record 26 is in the right data leaf node, and then we go to the right data leaf node. From there we go to directly to the record. Index seek is an operation where you jump straight into the record you want using an index. But let's have a look at a different type of operation, like a range scan operation. Let's say you want to find record from employee IDs 20 to 40, a range of employee IDs. So our query will be like this, and then we again start from the root node. In the root node, we find out that starting employee ID 20 is in the left intermediate node. So we go to the left intermediate node. From the left intermediate node, we find that starting employee ID 20 is in the right data leaf node. So we go to the right data leaf node and we don't find the 20, but we find 21. So we start reading from 21, and then we, using the double link pointers in the data leaf node, we go to the third data leaf node. In the third data leaf node, our read operation continue until we find record 38. There's not 40 employee ID, so we stop at the 38. So that's how range scan operation is carried out on a clustered index. When we create the clustered index, it's so that records are sorted on employee ID order. Because we specified employee ID as the key of the index, this is the data is going to sorted on employee ID. But let us say we have most queries written to find records by name. So we need another index where records are sorted on name column. That's where non-clustered index comes in. Non-clustered index are using the same data structure as the clustered index, which is B plus tree. Let us consider a scenario where we want to create non-clustered index on same employee table as above. We will create a non-clustered index on name field. So our SQL statement to create the index will be like this. As you can see this time, index type is non-clustered. Once index is created, leaf level of the non-clustered index will be like this. Note that now index rows are sorted on the name column and have a pointer to the primary key of the clustered index, i.e. employee ID. In addition to that, non-clustered index can have included column. For example, you can have age column in the index. If you include age column in the index, values of the age column will be on the data pages of the non-clustered index. Since non-clustered index carry less columns than the table, one page will be able to hold more rows than the clustered index. This is illustrated in above picture by showing 6 rows in the single page. As mentioned before, non-clustered index leaf pages have pointers to cluster index, as you can see in this screen. In this screen, you can see that Alice Johnson's record is pointed to the same record in the clustered index. Same way, other records are also pointed to related record in the clustered index. For clarity, we have not shown them here. Non-clustered index also have intermediate and root nodes. Same as the clustered index, non-clustered index intermediate nodes contain pointers to data pages, but this time they are sorted on different column, i.e. name column. Root node is also same and contain pointers to intermediate level pages. Now we know how the non-clustered index looks like in the disk. Let's look at how common operations are carried out in this structure. For example, let's say we want to retrieve records for Oscar Wilde. If we use a non-clustered index, we will have to scan entire table or the index. But if we use non-clustered index on the name column, we can directly go to Oscar Wilde record. To seek Oscar Wilde record, SQL Server starts from the root node. and from the root node it figure out records starting with O are in second intermediate node. Therefore it goes to right intermediate node. From the second intermediate node, SQL Server find out O's are in third leaf node. Therefore it goes to there and fetch the record. If query require only name and ID, non-clustered index itself will be able to satisfy the query and the operation will be complete. However, if query require additional fields which are not in non-clustered index, SQL Server can use the pointers in the non-clustered index to go to clustered index to fetch additional columns. This is called a key lookup operation. Let's take a look at different kind of a non-clustered index. A covering index. Covering index is an index which has all columns that require to satisfy a query without referring to base table, i.e. without key lookups as mentioned previously. Because covering index satisfies a query by itself, I/O requirement to serve the query is less. If all fields to satisfy the query is not in non-clustered index, SQL Server has to do key lookups and go to clustered index to pick missing fields. For example, let's consider a query like below. This query looks for employee name Hannah Lee and need to find her age as well. If we have a non-clustered index like one shown here, we can find the record easily by seeking to Hannah Lee using the index. But since index doesn't have an age field, SQL Server need to do a key lookup using pointers in the non-clustered index to clustered index and get age field value from the clustered index. What if we include the age column in the index, like using a statement like this? So we need to create non-clustered index again and include the age column like this. So once it's included, the non-clustered index will be like this. This is a non-clustered index on a name column, but additionally it has included age column. Note that age column is not part of the index key. Therefore, index will not be sorted on age column. It is just part of the index data rows. When query runs, SQL Server will use our index. It will do a seek on Hannah Lee's record as shown above. And query needs age value as well. Luckily, age value is also on the non-clustered index. So SQL Server can return the results without even touching the clustered index. Okay, today we have touched on SQL Server indexes. This module only covered very basic concepts related to indexes. Hope you enjoyed it and learned something. We will meet up with another module soon. Until then, have a good time. Thank you.